Now, when we're talking about solutions, we need to talk about how we measure solutions because we're scientists. And so we care about measurements and values. And in order to measure the concentration of a solution, so how concentrated the particles are in that overall solution, how concentrated the solute is in the solution, or how concentrated the solute is compared to the solvent, because sometimes we kind of do both, then there's a number of different concentration units that we can use. We'll kind of get into what we usually think about as chemists in terms of the SI unit for concentration, but there are many different applications, and there are many different applications, both industrial and chemical, that require different unit types. So I'm going to kind of run through some examples and work some problems with the different concentration units, and then we'll kind of go from there. So the first is mass volume percent, which I think is kind of a silly unit personally. This percent concentration, then, the mass volume percent, is equal to the grams of solute. So remember, the solute is the thing that's being dissolved, divided by the milliliters of solution. So that's the total amount. When you mix them together, the total volume of the solution, then hence the volume part, compared to the grams of the solute that you put in. And then you multiply that, because it's a percentage, because it's going to give you a ratio, which is going to look like a decimal. You multiply that by 100, and that gives you that percent. Now, the reason I think that this unit is a little bit silly is because grams per milliliter is a density, right? Which, it's silly and it's not silly. It's silly because it makes sense, because concentration is a measure of the density of the solute in a solution. So it makes sense that you'd use that, but why not just call it a density, I guess, for me? And we can use it in the same way that we've used densities in the past. Densities, because they give you a way to convert from grams to milliliters, this gives you a conversion factor that you can use to convert from mass to volume. So it's useful in that way, but now we have kind of a different application, because now we're talking about a mixture of things, a solution. So let's look at how we'd calculate this. This is asking for the mass volume percent of a 0.5 liter solution made with 12 grams of KBr. So we're looking at a solution of potassium bromide. We're going to take the number of grams that we're given of our potassium bromide, and we're going to divide it by the milliliters of solution. So this is a 0.5 liter solution. We know that there's 1,000 milliliters in 1 liter, so that would give us a 500 milliliter solution. My notation there is SOL with an apostrophe N. That's kind of a shorthand for solution. And then when we multiply this by 100, then this is going to give me 2.50% mass volume of KBr. Okay, and again, 3 significant figures, because we have 3 here from our mass, we have 3 here from our volume. I guess we can make this clearer or less ambiguous by either putting the decimal point there or calling that 5.00 times 10 to the second milliliters. That would kind of indicate your 3 sig figs, which gives you your 2.50 at the end. Now, another one that's really useful, and we see a lot for solutions, is mass percent, or mass over mass percent. So this is a similar kind of operation. This is going to be the mass of the solute over the mass of the solution. So this is really a percentage in the way that we normally think about it, right? It's the part out of the total, and we'll multiply that ratio by 100, and that's going to give us that percentage. Sorry, I'm a little bit crooked here. Okay. So mass percent is a pretty common way to do that. You might see a 3% solution of sodium chloride, for example, and that means that you have 3 grams of sodium chloride for every 100 grams of solution. So that's just kind of a shorthand way to do it. It gives you a quick ratio, and I think that we're used to thinking about percentages, and because we're comparing mass to mass, it doesn't really matter if we use grams or kilograms or megagrams. It just has to be the same unit, either one. So let's calculate the mass percent of copper in a bronze bell. So bronze is made up of copper and tin. So we want to calculate the mass percent of copper in my bronze bell given these masses. So since these are my masses, this is really useful actually in terms of solutions that are non-aqueous solutions. So a solution of metals, right, would be a mixture of metals. which is called an alloy. So alloys of metals are mixtures of metals, and bronze is copper and tin, like the Bronze Age. So we'll take the part, which it's asking for copper specifically. So we're going to take our 25 kilograms of copper, and we want to divide it by the mass of the solution. So we want to divide it by the mass of the total. So this would be 25 kilograms plus my 39.5 kilograms. That gives me my total in my solution, and then we'll multiply by 100 in order to give us a percentage from that ratio. And then when we do that, we have 3 sig figs here, 3 sig figs here. When we add them, we'll get 3 sig figs. So when we divide, we'll end up with 3 sig figs, and I got 38.8%. And then we can indicate that it's mass over mass, or we could call that a mass percent of copper, either way. All right, now there's many other concentration units that are used in, again, a number of different applications. When you're talking about very small amounts, you will often see units of parts per million or parts per trillion. So you'll see this as ppm or ppt. You'll also see, for slightly less or slightly more concentrated, because these guys are really tiny, you'll also see parts per thousand sometimes. So if you're thinking about this in terms of kind of either mass over volume or mass over mass, then parts per million would be milligrams per liter or milligrams per kilogram for thinking about it in terms of a solution. And then parts per trillion would be nanograms per liter or nanograms per kilogram, and that would give you a parts per trillion ratio. If you're doing parts per thousand, which I don't have here, I guess I could write that, parts per thousand. Then that's actually going to be a gram per liter. So gram per liter or gram per kilogram. We're thinking about mass to mass. So if you have just a solution that's something ppm or something ppt, or sorry, parts per thousand is kind of a pp. This one's a little less common because grams per liter is really something that's just a little bit less. Parts per trillion is the PPT. You'll see it as parts per thousand also. Doesn't really matter. But the parts per million and parts per trillion are for very small trace amounts of things. So you'll see them more in kind of research labs where you're looking at really small amounts in a very large solution, and where you're just not looking at as large amounts of, like, you know, kilograms and grams worth of material. So we're just talking teeny tiny. All right, speaking of teeny tiny, let's talk about moles. Of course, moles themselves are not teeny tiny, but they're talking about a large quantity of teeny tiny particles. And so I really think about molarity as the SI unit for concentration, because molarity is the number of moles of your solute that you have per liter of solution. Moles per liter. And molarity is abbreviated with a capital M for molarity. So moles of solute per liter solution. And so if you have something like, you know, here's a reagent bottle, and on the reagent bottle, there's the cap, because we're safe. It says something like 6.5 molar HCl. Then that means 6.5 molar HCl means that I have 6.5 moles of HCl per every 1 liter of solution. So this is kind of a useful tool, especially if we're going from moles to liters or liters to moles. So if we have some volume and we're trying to figure out how many particles are in there, or even then to get to a mass of how much I should put in there in order to make a solution like this, then molarity is really useful. Okay, so let's look at how we'd calculate the molarity. So we have a 2.1 liter solution made with this many grams of sodium chloride. So we take our 2.54 grams of sodium chloride. And I don't need a mass here, I need moles. So I need to go to the periodic table and use the molar mass of sodium chloride, which when I add together the molar mass of sodium plus chlorine gives me 58.44 grams of sodium chloride for every 1 mole. So that means that the number of moles is going to be, I got 4.19 times 10 to the negative 2 moles, keeping my 3 significant figures. And now for molarity, I'm going to take the number of moles that I have for the number of liters of solution. So I want that 2.10 total. 2.10 liters. And so that molarity is going to be 2.00 times 10 to the negative second molar NaCl. So not very concentrated, which is, you know, what we'd expect a liter if we picture liters, because we as Americans can actually picture liters because of 2-liter soda bottles, right? So if we picture half of our 2-liter of soda, and then we put 2.45 grams of salt in there, which isn't all that much. You can measure that out on a kitchen scale, no problem, and kind of see the magnitude of that. That's not a lot of particles in the solution, so it's not very concentrated, as opposed to some that might be more on the concentrated side of things. And we can also use it then to kind of get a volume if we know the number of moles. So if I have 0.051 moles of my nitric acid here, HNO3 is a hydrogen ion that's attached to a nitrate. This is an acid, so we call this nitric acid. So if we have this many moles of our nitric acid, and this is the concentration of my solution. I know that I have 0.952 moles of nitric acid for every 1 liter, so 0.952 moles per 1 liter of the nitric acid. Then my moles of nitric acid will divide out. I'll be left with an answer in liters, and it didn't give me a specific volume unit, so I ended up with this many liters, which looks like 2 sig figs from this guy, 3 sig figs from this guy, so we're going to be limited to 2. So let's go 1, 2, we're going to round up, 5.4 times 10 to the negative 2 liters. Okay, so you can kind of see the utility then of these concentration units. We can talk about how much solute we have in our solution. We can talk about whether the solution is concentrated or more on the dilute side. So that's kind of the opposite of concentrated, is more dilute, meaning more water. That's specific for aqueous solutions, and we'll talk about dilution calculations in a future video. And this also gives us then a method. When we have a ratio, whether it's the ratio of moles to liters, so if we have a molarity here, or if we have something like our mass to volume units, grams to mils, or our mass to mass units where we have grams to grams or kilograms to kilograms, or our parts per million, parts per trillion, then these all give us a way to convert from units of volume to either units of mass or units of moles. So depending on what we're given, we can find quantities, or we can figure out how to make those types of solutions pretty easily in a lab, which is just really handy. So if you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.